Hello, I'm Guruprasad Upadhya. So in the module 5, fifth module of 18MAT31, the second part is calculus of variations. The calculus of variations, in that the functional is nothing but functions of the type integral x1 to x2 f of xy y dash dx, that is called functional. Maximizing or minimizing the functional is called variational problems. So it is nothing but to find the curve y equal to y of x, where y at x1 is y1, y at x2 is y2, such that for a given function f of xy y dash, the functional integral x1 to x2 f of xy y dash dx is a stationary value. Stationary means either it is a maximum or minimum, or simply we can call it as extremum. If this functional is extremum along the curve y equal to y of x, that is our aim to find this function y equal to y of x. That means this functional is extremum along the curve y equal to y of x. Therefore, along the curve y equal to y of x, delta of x1 to x2 integral f of xy y dash dx must be 0, because it is extremum. So derivative is 0, or change in this is 0. So either it is maximum or minimum. Now, Euler's equation. So what is meant by Euler's equation? A necessary condition for a functional I equal to x1 to x2 integral x1 to x2 f of xy y dash dx to be extremum is that f by dou y minus d by dx of dou f by dou y dash equal to 0. Now here, if you treat f is a function of three variables x, y and y dash, differentiate this f partially with respect to y, treat x and y dash is constant, minus d by dx, this is total derivative of dou f by dou y dash, partial derivative of f with respect to y dash, treat x and y constant. So this is equal to 0. So this is Euler's equation. That means if f satisfies these conditions, then you are able to find the curve y with this condition. So along the y, I becomes extremum, either it is maximum or minimum. How to prove this one? Now the proof. Let y equal to y of x be the curve joining the points a x1 y1, b x2 y2, which makes I an extremum. That means along this curve y equal to y of x, this I is extremum, either maximum or minimum, or it is stationary value. Okay. Let y equal to y of x plus epsilon eta x be a neighboring curve joining these points. Here y equal to y of x plus epsilon eta x. Epsilon eta x means neighborhood of this curve. That means the joining a and b, I am going to take one more curve. It's very close to y equal to y of x. To separate this curve, so I am going to use one more function of x, but that function of x, eta x, it is from a to b. Therefore, eta x1 is 0, eta x2 is 0, because y equal to y of x plus epsilon eta x. Now this curve is the point of intersection of this curve and this y equal to y of x is same. At a and at b, y equal to y of x. That means this part is 0. Now epsilon is one more variable we taken. Therefore, eta x1 is 0, eta x2 is 0. So eta x1 and eta x2 become 0, because this y equal to y of x plus epsilon eta x is also a curve joining the point a and b. Now this I along this curve becomes, here x is x only, y is nothing but y of x plus epsilon eta x, y dash is nothing but y dash of x plus epsilon eta dash x into dx. The value of I along y equal to y of x plus epsilon eta x is I equal to integral x1 to x2 f of x comma y of x plus epsilon eta x plus y dash of x plus epsilon eta dash x dx. Now here f is a function of here three variables x, y and y dash, and I is function of x and epsilon, because here epsilon eta x is a function of x, yx is function of x, y dash is also function of x, eta dash is also function of x, and one more variable is epsilon. Any functional or any function, if it is extremum, then derivative with respect to epsilon is 0 here. Similarly, derivative with respect to x is also 0. Here this functional is extremum if di by d epsilon is 0. Since I is function of epsilon, I is extremum if di by d epsilon equal to 0 at epsilon equal to 0. Now, how to find di by d epsilon? By the derivative under integral sign. Here it is partial derivative of f with respect to epsilon, but f is function of three variables x, y and y dash. By the total partial derivative, so that you studied in first sem, so it becomes dou f by dou x into dou x by dou epsilon plus dou f by dou y into dou y by dou epsilon plus dou f by dou y dash into dou y dash by dou epsilon. So this is the total partial derivative because f is function of x, y and y dash, but you are differentiating partially with respect to epsilon. So through x, through y and through y dash you are going to find the partial derivative. But here f is function of x and epsilon. Finally, it is function of x and epsilon. When you differentiate partially with respect to epsilon, treat x constant. Therefore, dou x by dou epsilon is 0. And you know that y is y of x plus epsilon into eta x. So partial derivative of y with respect to epsilon is, partial derivative of y with respect to epsilon is, derivative of epsilon is 1 into eta x. Similarly, partial derivative of y dash with respect to epsilon is eta dash x. Now substitute dou x by dou epsilon, dou y by dou epsilon, and dou y dash by dou epsilon. See here, y equal to y of x plus epsilon eta x, partial derivative with respect to epsilon. So 1 into eta x because you are treating x is constant. And similarly, dou y dash by dou epsilon is eta dash x, 1 into eta dash x. And when you are going to differentiate partially with respect to epsilon, treat x constant, therefore this is 0. So this part is 0 and only these two parts. Here you are going to substitute eta x, this is eta dash x. Therefore, di by d epsilon becomes x1 to x2, integral x1 to x2 eta x dou f by dou y plus eta dash x dou f by dou y dash. Now, apply the product rule or integration by parts for the second one. First one keep as it is. So integral x1 to x2 eta x dou f by dou y dx plus integral x1 to x2 eta dash x dou f by dou y dash dx. Now first function is dou f by y dash, second function is eta dash x. Integral of the second is eta x. Derivative of dou f by dou y dash is d by dx of dou f by dou y dash. Therefore, the integral of this becomes first function into integral of the second, that is eta x, and limit is from x1 to x2 minus integral derivative of the first function d by dx of dou f by dou y dash into integral of the second, that is eta x. Now this part, we know that eta x1 and eta x2 both are 0 for the upper limit, and for lower limit this part becomes 0. Now combine these two once again. x1 to x2, common term is eta x, take outside dou f by dou y minus d by dx of dou f by dou y dash into dx. So this integral becomes integral x1 to x2 eta x dou f by dou y minus d by dx of dou f by dou y dash into dx. Now I is extremum if this must be 0. Eta x is variable functions, it is neighborhood functions, therefore this function di by d epsilon is 0 if and only if this part is 0. That means dou f by dou y minus d by dx of dou f by dou y dash is equal to 0. So remember this formula, Euler equation. So partial derivative of f with respect to y minus d by dx of partial derivative of f with respect to y dash, this must be 0. This is Euler's equation. And with the help of the total partial derivatives for some result, we are able to express the same Euler equation in two different forms. So other forms of the Euler's equations, that is d by dx of f minus y dash into dou f by dou y dash minus dou f by dou x equal to 0. This is one more form, and one more is dou by dou y minus dou square f by dou x dou y dash minus y dash into dou square f by dou y dash minus y double dash into dou square f by dou y dash square is equal to 0. Why these other forms are required? It is just applying the partial derivatives twice, we will get this form, the same Euler's equation in this form. Okay. Now, when you are going to solve the problems or to find the functional where the functional is maximum or minimum, extremum value of the functional, to find the extremum value of the functional, so you are going to directly use Euler's equation. And also, if the f is independent of x, suppose f is independent of x, then the solution is f minus y dash into dou f by dou y dash equal to constant, because if it is independent of x, partial derivative of f with respect to x is 0. This part is 0, not total derivative, the partial derivative is 0. Therefore, take dx right side. So d of f minus y dash dou f by dou y dash is 0. Integrating, we will get f minus y dash dou f by dou y dash is constant. So remember only this. This becomes Euler equation if f is independent of x. So it is shortcut method to solve the functionals. See careful here. First you check whether f is independent of x or not. If it is independent of x, immediately just find dou f by dou y dash only. Then f minus y dash into dou f by dou y dash, let it be some constant. Then simplify it and then integrate, find the value of y where this functional becomes maximum. One more is if f is independent of y, so use the first one. So dou f by dou y is 0. So d by dx of dou f by dou y dash is 0, or d of dou f by dou y dash is 0 means dou f by dou y dash is constant. It is from the first what we derived first, that Euler equation, we got dou f by dou y dash is constant if f is independent of y. And one more is if f is independent of y dash, suppose f is independent of y dash, then immediately Euler equation becomes dou f by dou y is 0, because in the first Euler equation dou f by dou y dash d by dx of dou f by dou y dash, that part is 0, only first part dou f by dou y becomes 0. So this is Euler equation if it is independent of y dash. And finally, remember one more one, if f is independent of x as well as y, see this is another form of the Euler equations. If it is independent of x and y, see this is 0, partial derivative with respect to y is 0, with respect to x is 0, with respect to y is 0, only this part. So y double dash dou square f by dou y dash square is equal to 0. But dou square f by dou y dash square, it cannot be 0, therefore y double dash is 0. Therefore Euler equation becomes y double dash is 0. Immediately you integrate, you get the straight line. If f is independent of x and y, y double dash equal to 0 is the Euler equation. So this is some shortcut method to find the extremum of the functional. So depending on f. Now we will discuss some problems direct problems. Find the curves on which the functional integral 0 to 1 y dash square plus 12xy into dx with y at 0 is 0 and y at 1 is 1 can be extremized. Can be extremized means with these conditions, this functional is either maximum or minimum. Along which curve this functional is either maximum or minimum. Find that curve or curves. So it depends on the problem. Here it is one curve is required because endpoints are given. Y at 0 is 0, y at 1 is 1. So we get one curve. Along that curve, this functional becomes maximum or extremized, or it is maximum or minimum. Now here f is y dash square plus 12xy. F is y dash square plus 12xy. So partial derivative of f with respect to y, when you are going to differentiate f partially with respect to y, treat x and y dash constant. So this part becomes 0 because it is constant. Derivative of y is 1 with respect to y, derivative of y is 1. So remaining term is 12x. Therefore, dou f by dou y is 12x. And dou f by dou y dash is, when you are differentiating partially with respect to y dash, x and y are constants, so this derivative is 0. So 2y dash, that's all. Because partial derivative with respect to y dash, therefore it is 2y dash. Now you differentiate 2y dash with respect to x. This is not partial derivative, total derivative. D by dx of dou f by dou y dash. Now dou f by dou y dash is 2y dash. Again y dash is nothing but dy by dx. Again d by dx of dy by dx is d square y by dx square. That is y double dash. 2y double dash. So d by dx of dou f by dou y dash is 2y double dash. Now substitute these two values in the Euler's equation. So Euler equation is dou f by dou y minus d by dx of dou f by dou y dash is equal to 0, and this one is dou f by dou y is 12x minus 2y double dash equal to 0. Now see this, 2y double dash is 12x, y double dash is 6x. Now y double dash is 6x. Therefore, if you integrate y double dash, you will get y dash. Integration of x is x square by 2. Cancel 2, 3x square plus integrating constant, let it be a. Here y dash is nothing but dy by dx. Again integrate, take dx here, integrate this, so you will get y. Integration of x square is x cube by 3, cancel 3, so x cube. Integration of a with respect to x is ax plus integrating constant b. Now with the help of these initial conditions y at 0 and y at 1, boundary conditions y at 0 and y at 1, find the value of a and b. When x is 0, y is 0, put x is 0, y is 0, then b becomes 0. So b is 0. Next, when x is 1, y is 1, put y is 1, x is 1. 1 equal to 1 plus a, because b is 0. 1 equal to 1 plus a, take 1 left side, 1 minus 1 is 0. So a is also 0. A is 0, b is 0 means required the function is y equal to x cube. So along y equal to x cube, this functional is either maximum or minimum. Now see, at y equal to 0, at x equal to 0, y is 0, at x equal to 1, y equal to 1, by substituting it will b becomes 0, a is also 0. The required solution is y equal to x cube. Follow? No, it's a very simple logic. Just remember this formula, Euler equation, and see the partial derivatives. It is not complicated one, very simple partial derivatives. Okay. One more example. On which curve the functional 0 to pi by 2 y dash square minus y square plus 2xy into dx with y at 0 is 0, y at pi by 2 is also 0, be extremized. That means this functional is either maxima or minima along some curve. Find that curve. To find that curve, so here f is y dash square minus y square plus 2xy. So y dash square minus y square plus 2xy. Here it is not independent of x, y or y dash. Therefore, no need to worry. Directly use the Euler equation. So dou f by dou y. First you differentiate partially with respect to y. This is 0 minus 2y plus 2x minus 2y plus 2x. Dou f by dou y dash. Here no y dash 0, here 0, y dash square derivative 2y dash. Again differentiate 2y dash with respect to x, that is total derivative. So d by dx of dou f by dou y dash. So that is 2 into y dash derivative y double dash. Now substitute these two in the Euler equation. So it becomes dou f by dou y minus 2y plus 2x minus 2y double dash. Now cancel 2 throughout. Y double dash plus y equal to x. See this, cancel 2 throughout. Take minus y double dash right side and y also right side. So it become plus y double dash plus y equal to x. How to solve this? So you already solved these type of problems in second sem. Y double dash plus y. So we can write in symbolic form d square plus 1 into y. That is equal to x. You know that auxiliary equation d square is minus 1, d is plus or minus I. Therefore, yc is c1 cos x plus c2 sin x. D square is minus 1, d is plus or minus I. Therefore, complementary function yc is c1 cos x plus c2 sin x. So, I taken here a and b. Okay, a cos x plus b sin x. How to find yp? 1 by d square plus 1 of this x. 1 by d square plus 1 of x. By long division, you are taking x. 1 plus d square. First term is x. 1 into x is x. Second derivative of x is 0. Therefore, x minus x is 0. Therefore, 1 by d square plus 1 is x. D square plus 1 of x is x. Now, add these two. So, complete solution is y equal to a cos x plus b sin x plus x. To find a b value, put x is 0, y is 0. 0 equal to a into 1 plus b. 0 equal to a into 1. See here, cos 0 is 1 plus sin 0 is 0. This part is 0, x is 0. Therefore, a into 1, that is y. Y is nothing but 0. Therefore, a becomes 0 and hence the y becomes b sin x plus x. Now, how to find this b value? A is 0, cancel this and substitute the another condition. Put x is pi by 2, y is 0. 0 equal to, this a is already 0, b into sin pi by 2. Sin pi by 2 is 1, b plus pi by 2 equal to 0. B plus pi by 2 equal to 0 means b is minus pi by 2. And hence, the solution, required solution is y equal to x plus b. B is minus pi by 2. X minus pi by 2 sin x. A is 0. Follow now? So, very simple logic. Go through this. And one more, little bit complicated. That means to find the solutions. That is actually second sem concept. Solve the variational problem delta of 1 to 2 x square y dash square plus 2y x in 2y into x plus y dx. This is 0. It is nothing but integral 1 to 2 x square y dash square plus 2y into x plus y dx is extremum, either maximum or minimum. Therefore, this delta is 0. Given that y at 1 is 0 and y at 2 is 0. Y at 1 is 0, at 2 is 0. Now, how to solve this function? Here f is x square y dash square plus 2yx plus 2y square. So, x square y dash square plus 2yx plus 2y square. Differentiate f partially with respect to y. Here no y, 0. Here 2xy derivative with respect to y is 2x. And 2y square derivative with respect to y, partial derivative with respect to y is 2y square derivative is 2 into 2y, that is 4y. And partial derivative of f with respect to y dash square derivative 2y dash. So 2x square y dash. Differentiate this with respect to x, not partial, total derivative. D by dx of 2x square y dash. Use the product rule. 2x square into y dash derivative y double dash. 2y dash into derivative of x square 2x. 2 into 2x 4x y dash. 4x y dash. Now substitute these two in Euler equation. That is dou f by dou y minus d by dx of dou f by dou y dash equal to 0. So this minus this equal to 0. 2x plus 4y minus 2x square y double dash plus 4xy dash equal to 0. Now either you cancel 2 common or 2x square y double dash plus 4xy dash equal to 2x plus 4y. Take 4y left side. Now equation becomes x square y double dash after cancelling 2xy dash 2y minus 2y. When you take this right side, it is minus 2y equal to x when you divide by 2. Now this is Cauchy equations. Cauchy equations that you studied in second sem. X square y double dash plus 2x y dash minus 2y equal to 0. Put x equal to e power t. T is log x. X y dash is capital D y. X square y double dash is d into d minus 1 y. And then it reduces to the equations with the constant coefficients. Then you know how to solve. Okay. Put x equal to e power t. T is log x. X y dash is dy. X square y double dash is d into d minus 1 y. And hence x square y double dash is d into d minus 1 y. 2 into xy dash is dy minus 2y equal to x is nothing but e power t, or d square minus d plus 2d is plus d square plus d minus 2y equal to e power t. Now this is function of y and t with the constant coefficients. Auxiliary equation is d square plus d minus 2 equal to 0. Find the roots of the auxiliary equations. Roots are 1 and minus 2. Therefore, y equal to c1 e power 1t plus c2 e power minus 2t, or you can write yc is a e power t plus b e power minus 2t. Yp is 1 by d square plus d minus 2 of e power t. Put d equal to 1. 1 plus 1 minus 2. This becomes 0. Therefore, t into 1 by f dash d 2d plus 1 of e power t. Again put t is 1. So 2 into 1. 1, 2 plus 1 is 3. So t e power t by 3. And add these two. The complete solution is ax. Why it is x? E power t is x. So I want the solution of the given. That means not this one. This is modified one. Now put e power t is. Go back to the previous equation. E power t is x. E power minus 2t is x power minus 2 e power t whole power minus 2. X power minus 2 is 1 by x square plus t. T is log x. E power t is x. So x log x by 3. So this is our required answer. But how to find a and b? Apply the given conditions. Y at 1 is 0, y at 2 is 0. Put x equal to 1 and y equal to 0 first step. When x equal to 1, log 1 is 0. Therefore, a into 1, that is a, b plus b by 1, that is b, a plus b is y, that is 0. A plus b is 0. When x is 2, a into 2, that is 2a, b by 2 square, that is b by 4, 2 log 2 by 3 equal to y. Y is 0. Now, just multiply throughout by 8, 4, 2 into 4 is 8a plus b plus 8 log 2 by 3 equal to 0. Therefore, 8a plus b equal to minus 8 log 2 by 3. Since b is minus a, 8a minus a is 7a. Therefore, a is dividing by 7 means denominator is 21. A is minus 8 log 2 by 21 and b is minus a. See this, b is minus a and hence b is 8 log 2 by 21. A and b are similar, but a is negative, b is positive. See here, a is negative, b is positive means take that common term outside and interchange this. Therefore, required solution is 8 log 2 by 21 into 1 by x square minus x. See, 1 by x square, because b is positive, I am going to write first. And a is negative, therefore 1 by x square minus x. So, this is required solution. Now, one more example. Prove that the shortest distance between the 2 points in a plane is a straight line. So, it is obvious, it looks fine. But how we can prove shortest distance between 2 points in a plane? In a plane, take any 2 points and find the curve joining A and B and see the shortest distance. Minimize that curve, length of the curve. When you minimize the length of the curve, that curve becomes straight line. This is the logic. Let A x1 y1 and B x2 y2 be the given points and S be the arc length of the curve connecting them. Okay. Here A and B are the given point on the plane and this S is the arc length of the curve. Okay. This curve connects A and B, not this dotted line, this S. And we have one formula, ds by dx is square root of 1 plus y1 square or y dash square. So, that is ds. Integral of ds from x1 to x2 is nothing but s. So, arc length s becomes integral of ds and ds by dx is square root of 1 plus y dash square. So, this is first same formula. So, it is there. Derivative of arc with respect to x is square root of 1 plus y dash square or dy by dx whole square. Now, ds is nothing but root 1 plus y dash square into dx. Replace ds by root 1 plus y dash square into dx. Now, the question is shortest distance between 2 points. This arc length must be least. So, extremize means minimum of s. To find the minimum of s, apply the Euler's equation for this f. Here f is nothing but square root of 1 plus y dash square. Now, s will be minimum if it satisfies Euler's equation. If it satisfies means this f function satisfies Euler's equation. What is that function? F is root 1 plus y dash square, which is independent of x and y. No x, no y. Immediately Euler equation becomes y double dash is 0, that you know, that we discussed in the previous. Okay. Since it is independent of x and y double dash is 0 is the Euler equation. Euler equation reduces to y double dash is equal to 0. Okay. Now integrate y double dash. So it is y dash is constant. Second derivative 0 means first derivative is constant. Again integrate. Derivative of m is x, mx plus integrating constant 0. Therefore, y equal to mx plus c. Clearly, this is the curve. You know that y equal to mx plus c is a straight line. Therefore, along this straight line, the distance between a and b is the shortest one. If you take any other curve, its distance is more in that plane only. So, don't take any other surfaces along the plane and take any curve joining A and B, and its distance minimum if and only if that curve becomes straight line. So, this is the logic. Okay. I hope you got the idea how to solve the Euler equations to find the extremum of the functional. Now, still we have some more types of functionals, that means hanging chain problems and geodesic and all those are there. So, that I am going to discuss in the next video. Thank you for listening.